You are witnessing the biggest paradigm shift in physics for 30 years. Evidence is mounting that the cosmological constant is in fact not constant. Rather than dark energy, which is already weird, it seems to be a type of phantom energy. This is an update on a story which we talked about already last year. A paradigm shift starts with, "Ha, that's funny," turns to curious and curiouser, before the final stage that's technically known as the well damn phase. Last year we were at, "Ha, that's funny," and we're now at curious and curiouser. This research is about dark energy. That's the name physicists have given to whatever it is that speeds up the expansion of the universe. It's not just that it makes the universe expands, normal matter does that too. Dark energy accelerates the expansion. There were indications of this already in 1990. This was the "ha, that's funny" phase. By 1995, the community was in the curious and curiouser phase, and by 1998 they reached the well damn phase and accepted that dark energy is real. Dark energy should not be confused with dark matter or black holes. Dark energy is what accelerates the expansion of the universe. Dark matter makes galaxies rotate faster, and black holes are what politicians call it if they misplace a few $1 billion. But dark energy, dark matter and black holes could be related. More about this later. The simplest type of dark energy is the cosmological constant, which, as the name suggests, doesn't change in time. The cosmological constant is a constant of nature, like the strength of gravity. Or so we thought, because new data say it isn't constant. The new data come from the Dark Energy Spectroscopic Instrument, DESI, located atop Kitt Peak in Arizona. It's one of the most extensive surveys of what's inside our universe ever. The new analysis uses data from DESI's first 3 years of observations, in which they took images of nearly 15 million galaxies and quasars. In these images, they look for patterns in the distribution of galaxies, the so-called baryon acoustic oscillations. These are left over from sound waves in the plasma in the early universe. From this, they can extract the amount of dark energy at different times. They'd previously found tentative evidence that dark energy had been weakening over time, which I talked about last year. The new thing is now that not only is it getting weaker today than the cosmological constant would be, but that in the past it must have been stronger than a cosmological constant could be. In their new paper, they quantify this by the ratio of the pressure over density, which is a parameter called W. For the cosmological constant, this W is equal to -1. You can see the results of their analysis in this figure. The dashed line is the prediction for a cosmological constant. The grey line is the best fit to the data, and the grey shaded regions are the 1 and 2 sigma uncertainty ranges. In this figure, the current time is on the left and the distant past is on the right. So you can see that currently the ratio isn't as negative as it should be, and in the past it must have been even more negative than the cosmological constant. If that happens, it's called phantom energy, and the crossover is called a phantom crossing. It's like a zebra crossing, just without the zebra. Combined with other data from the CMB supernovae and weak lensing, the evidence for this is now at 4.2 sigma, depending on how you look at it. Not quite well damn yet, but definitely curious. So it looks like the universe had phantom energy in the past, but no longer has. What does it mean? For one thing, it tells us something about the ultimate fate of our universe. If dark energy is constant, then the expansion of the universe will keep on accelerating forever. Eventually, it'll tear everything apart, even atoms. It's sometimes called the Big Rip. But if dark energy weakens, as seems to be the case, or goes maybe even all the way to zero, the acceleration can decrease, stop, and even reverse. So our universe might end up instead in a recollapse, maybe even followed by a new Big Bang. By the way, this video comes with a quiz that lets you check how much you remember. But if dark energy is not just a cosmological constant, then what could it be? One possibility is that it's a condensate of tachyons, that are particles which travel faster than light, because these can have rather weird properties like this negative pressure. It could also be that dark energy decays to dark matter, so these two might be related. In an earlier video, we also talked about the idea that dark energy is a kind of vacuum pressure created by black holes. Interestingly, this idea is not compatible with the new data because it wouldn't give you this phantom energy range. So it seems like the expansion of the universe might have been powered by phantom energy. If nothing else, I hope we can at least agree that physics has the coolest words. Hello? Hi, Elon. No, you can't power a rocket with phantom energy. Well, because it's no longer there. Ah, they've used it up? That's brilliant. You should submit this to Nature. Soon, you'll be rich and famous. Love you too. Former Google CEO Eric Schmidt is one of the authors of a new strategy paper that says we're well on the way to mutually assured AI malfunction. Much like the mutually assured destruction of nuclear war, the threat of a disastrous retaliation, they say, will prevent anyone from developing superintelligent AI. Simply put, they're saying we must prepare to sabotage others' research projects. I'm not making this up. Let's have a look. Artificial intelligence is a very dangerous technology that can potentially kill a lot of people very quickly. This could happen in many ways, most directly because bad actors use AI for military purposes, terrorist attacks or cyber attacks. But the problem might not be humans. The problem might be the AI itself. Once computer systems become more intelligent than we are, it'll be very difficult to control them. They might develop their own agenda. Maybe they already have. The threat is real. Unfortunately, AI safety has fallen by the wayside since Americans had their DeepSeek moment and Trump has removed what little safety requirements the USA had. So if not AI safety laws, then what? Well, this is where the new strategy paper comes in. It's titled Superintelligence Strategy. In it, Eric Schmidt and his co-authors say we are approaching a situation of mutually assured AI malfunction, MAME for short. Like the mutually assured destruction of nuclear war, it means that the threat of retaliation and escalation deters aggression in the first place. And in the case of AI, the aggression is the development of superhuman intelligence. They explain that MAME is a situation in which no power dares attempt an outright grab for strategic monopoly, as any such effect would invite a debilitating response. This strategic condition represents a potentially stable deterrence regime, and then they make recommendations for how to maintain this situation, which are, well, very blunt. They recommend that states need to improve their ability to attack AI projects of other states. In their own words, states could improve their ability to maim destabilizing AI projects with cyber attacks. They could identify AI developers' projects or collect information on the professional activities of AI developers, scientists. To spy on AI projects at most companies, all that's necessary is a Slack or iPhone zero-day software exploit. States could also poison data, corrupt model weights and gradients, disrupt software that handles faulty GPUs, or undermine cooling or power systems. They also recommend that states make their attack plans common knowledge, or as they write, clarify the escalation ladder of espionage and sabotage, because what good is deterrence if the enemy doesn't know they're supposed to be deterred? Furthermore, they say states should build data centers in remote locations. This is to make sure that if the enemy comes to bomb your AI, only the people who work there go up in smoke. I find this a very grim strategy for AI safety that paints a future in which we've given up even trying to collaborate. I must also say that I don't quite see how this would work in practice, because I don't think anyone can tell in advance whether a research project will get to superhuman intelligence. And if anything, at the moment, American companies are exaggerating how close they are. Though now that I think about it, maybe that's just a ploy to confuse the Russians. Let me instead tell you about a somewhat more optimistic and practical solution, which comes from Esther Dyson. She says that we should require AI companies to get insurance for damages that their products can incur. I find this a brilliantly simple idea because it A, creates an incentive for insurance companies to evaluate the potential harm of AI systems, and B, the insurance costs in return create an incentive for AI companies to make their products safer. The problem with this idea is that it'll make AI products more expensive than they already are, so I doubt that many people besides me will be enthusiastic about it. The underlying problem, though, is that we've heard so much about how AI is dangerous and can kill us all. We've just gotten somewhat tone deaf. It's turned into yet another old story that we've heard before. But I think they're right. Superhuman intelligence is going to change the world very quickly and not necessarily for the better. Then again, maybe those fears are overblown. If you want to get rid of a superintelligence, all you need to say is, what if everything in the universe is made of tiny wiggling strings? That ought to keep them occupied for a few decades. In December, a group of British scientists unveiled the first prototype of a battery that runs on nuclear waste and that could keep going for more than 5,000 years. Let's have a look. Nuclear waste is really an oxymoron, because if the material radiates, it means that it emits energy. So why bury the stuff in the ground, scientists say? Let's do something useful with it. NASA's used some sorts of nuclear batteries since the 1970s to power, for example, the Voyager missions. These are what's called thermonuclear batteries that turn heat from radioactive decay into electricity. However, this detour through heat is rather inefficient. This is why scientists have long tried to produce nuclear batteries that generate electricity directly from the radioactive decay. The new battery now comes from the company Arkenlight, which is a spin-off from the University of Bristol. They made a battery from carbon-14. This radioactive isotope is created in the graphite shielding of nuclear reactor cores. It makes better decay, so it emits an electron, and it has a half-life of 5,700 years. Worldwide, there are about 250,000 tons of this graphite waste, which could power a lot of batteries. Just how they create a battery from the carbon-14, I don't know, as they don't have any technical reports, but I have a guess. They probably evaporate the carbon-14 and mix it with a gas of the stable carbon isotope. Then they take one half and mix in nitrogen, and another half and mix in some other element, maybe phosphorus. Then they condense the stuff in 2 layers on some surface. These are basically synthetic diamonds. They need 2 different layers of crystal structures so that the random decay of the carbon-14 creates a directed electric flow. The result is what's called a beta voltaic battery. And around that you need some shielding so that the occasional stray electron doesn't harm anyone touching the thing. But this type of radiation is quite easy to shield. Just, don't chew on the thing. Similar batteries have been produced before, but with other isotopes and shorter half-lives. Arkenlight is the first to do it with carbon-14 from the graphite waste. This is why they recently made international headlines with their first prototype. So this is a pretty cool idea to turn nuclear waste into something useful. However, the power of such batteries is super low. The carbon-14 battery probably has a power production below a microwatt. You'd need 100 million or so of them to power your laptop. This might sound somewhat surprising because we always hear that nuclear power is so energy dense. But this is for nuclear fission reactors, which undergo controlled chain reactions. The batteries work entirely differently. They instead rely on radioactive decay. Still, even with such a tiny power output, these batteries have their uses because they have such a long lifetime. They could, for example, power medical implants. I believe that these will become dramatically more common in the near future. If you have any sort of risk factor, you'll get a teeny tiny device inserted that'll give an alarm if something goes wrong, or that can be used to regulate, say, stray electrical signals like pain or a heart arrhythmia or whatnot. In space, such batteries might keep sensors alive on missions to distant planets, or you could use them to power tags for satellite payloads to know where they fell down. Closer to home, it could be used to track ocean currents on the seafloor. This British battery isn't the first nuclear battery, of course, and while the diamond battery is still in the lab, the American company City Labs has been selling nuclear batteries for years. Their batteries use tritium, a radioactive form of hydrogen with a half-life of 12 years. They create up to 100 microwatt or so, which for nuclear batteries is actually a lot. Still, with a half-life of 12 years, these batteries don't last long enough for sensors that you want to remain active for hundreds, if not thousands of years. The CityLab batteries are already out there working. They power environmental sensors in places too remote for battery swaps, like weather stations in the wilderness. They say on their website that these batteries are also good for defense purposes because I guess they might accidentally drop into someone's tea. Looking at the big picture, it's interesting that this technology is only being developed now, when the basic ideas go back more than half a century. I think it's a sign of the overall nuclear renaissance that we're seeing. I'm sure it won't be long now until we can lean back in our autonomous, nuclear-powered flying cars and watch YouTube. I recently read a call for proposals from DARPA, a research agency of the US Department of Defense. They're asking for submissions of ideas for, quote, growing biological structures of unprecedented size in microgravity, by which they mean up to 500 meters. Wild. I looked into it, and while I didn't find any plans to breed kilometer-sized aliens in space, unfortunately, it made me realize that I've totally underestimated the pace of the space race. There is so much more going on there than I knew. I read the DARPA call, and it turns out the Americans don't plan to hatch dragons in orbit. Rather, they think that some biologically grown materials could be useful in space. The examples that they name are tethers for a space elevator, grid nets for orbital debris remediation, or patch materials. I think the idea is to set up some sort of base station which will then regularly be supplied with feedstock. That way you don't have to transport the entire product into space, but it assembles itself up there. DARPA also seems to include a bio-inspired self-assembly of mechanical structures, such as additional wings of a commercial space station or space-based interferometers. So these structures may not literally be alive, they may be produced by living organisms or be assembled like living organisms. It's not as crazy as it sounds at first. Indeed, they write in the proposal, a relevant analogy is that of a tent, which may be the most efficient anti-hype sentence ever. In their analogy, the cover of the tent may be biologically grown. The reason they're interested in this is that it's easier to transport basic materials in small forms and sizes into space and assemble them up there. Better still if the assembly is done by robots or happens more or less automatically. If spiders can produce lots of silk, why can't we use a similar idea to produce space tethers? I mean, come on, giant spiders in space. How cool is that? Well, the biological part of this idea would take some more time to work out, but I was surprised to find that the mechanical self-assembly in space is much further along than I thought. Multiple companies are already working on self-assembling space structures, and they have something to show for too. The first example I have is not a company, it's a non-profit organization called Aurelia Institute. They were founded in 2021 by alumni of MIT and SpaceX and are working on self-assembling and reconfigurable space habitats. These habitats build themselves from hexagonal elements that attach to each other. They already tested this idea with a small prototype in parabolic zero-G flights and also on the International Space Station to make sure that the assembly works properly. They yet have to bring the full-sized elements to space, but their plan is to get it done by the 2030s. They say that a habitat of 32 elements could host 4 people. You might say, well, if you need to keep air inside, maybe it's not such a great idea to build it out of modular elements. And I hear you. But at least in the near future, most of the work up in orbit will probably not be done by humans anyway, but by robots. This brings me to another interesting example. That's the California-based startup Crises. They've been around since 2018 and are also developing a modular orbital platform, but this one isn't meant for humans. They call it the port. The idea is that spacecraft land there, leave their payload, and robots assemble it in space. Last year, they demonstrated that their robot can assemble a small satellite from parts in just 1 hour. The port is also modular and can grow itself, so to speak. And of course, there is Axiom Space that's developing the world's first commercial space station, Axiom Station. It's the planned successor to the International Space Station, which is scheduled to retire around 2030. Their plan is to first attach a new module to the ISS, currently scheduled for 2027. Then they want to increase the new part and in 2028 detach it from the ISS. The new station is designed not just for research and development, but also space tourism. It features large windows, dynamic LED lighting, high-speed internet, and a glass-walled cupola for Earth viewing. Besides the companies working on habitats, there are also various startups that are developing 3D printers and assembly robots that can work in space. So I think where all of this is going is a real industry in space, and I've been surprised to see how far along some of those companies are already. Though personally, I think we should train tardigrades. Writing my startup pitch now. There are so many crises in cosmology now. I could talk about a new crisis development every day. That'll get tedious very quickly. So instead, I have a quick rundown with the biggest crises that you need to know about, including the most recent twists and turns. The most reported crisis has been the Hubble tension. That's a discrepancy between different measurements for the value of the Hubble constant, one of the parameters in the current standard model of cosmology, also known as lambda CDM. The data from the early universe, like the cosmic microwave background, gives a smaller value than those from nearby later data, like quasars or supernovae. And as the data have become better, the discrepancy has grown, not gone away. The newest development is that we're now officially allowed to call it a crisis after the lead author of a recent study, Dan Skolnick, declared that the tension now turns into a crisis. Finally, I've been wanting to use my In Case of Cosmological Crisis Break Glass emergency kit for years. Last year, I told you that the tension was somewhat alleviated by a study from the group of Wendy Friedman. It suggested that using data from the James Webb Telescope to readjust the measurements from the later universe, the result was compatible with that from the early universe. Already back then, New Scientist quoted the above-mentioned Dan Skolnick with saying that this doesn't feel like the current state we're in. In his recent paper, he's basically made sure to bring the Hubble tension back. His group made the most precise calibration ever of data from the late universe by exactly measuring the distance to a galaxy cluster called the Coma cluster. This could have confirmed the Friedman result and made the tension go away it didn't. The second crisis in cosmology is that the cosmological principle just isn't correct. This principle assumes that the universe is on average the same everywhere, and it's one of the assumptions for the current standard model for cosmology. Indeed, we can use this model to calculate just how large the biggest clumps of matter should be. The trouble is that astrophysicists keep finding clumps that are bigger than they should be. There is, for example, the Great Wall, a collection of galaxies about 1 billion light-years away from us that extends over 1.5 billion light-years. The huge quasar group, which spans 4 billion light-years, and then the recently discovered Big Ring that also spans 1 billion light-years. If our theories were correct, then these large structures shouldn't exist. Another piece of evidence against the cosmological principle is a discrepancy between two measurements of our own motion through the universe. You can do this either by measuring our motion against the cosmic microwave background or by using our motion against the average motion of distant quasars. This is related to the cosmological principle because to infer our own motion against the quasars, you need to know at what distance they'll be averagely distributed. The standard cosmological model tells you what this distance is. But if you use that, then these two measurements of our own motion disagree by almost 5 sigma. The third crisis is that the James Webb Telescope has discovered big galaxies that were around when the universe was only a few 100 million years old. These galaxies appear surprisingly massive and mature for their age. It's like you finally got to meet your 2-year-old nephew, but he's 6'3" with a beard. Somewhat surprising. Some of these galaxies even exhibit features like rotating disks, which were not expected to have formed so early. This is why you have seen countless headlines saying that these galaxies shouldn't exist. As we discussed in an earlier video, this was a prediction of modified Newtonian dynamics, but astrophysicists have trouble accepting this explanation. They've since proposed multiple alternative explanations that fit the cosmological standard model with dark matter. You can tell that this is a crisis just by noting that they came up with these explanations after the data came in. By the way, this video comes with a quiz that lets you check how much you remember. And the fourth and final crisis is the sigma 8 crisis. This is another discrepancy between measurements from the early and late universe, but this one is about a parameter, that's the sigma 8, which measures how much matter clumps over time. Basically, it hasn't been clumping enough. The interesting thing about all these crises in cosmology is that they only came into focus in the past 10 years or so, a development that's been entirely driven by data. It hasn't yet caused a major paradigm shift because for 99% of our observations, the standard model works. But that's like when a company says their update is 99% compatible with the previous version. It's that remaining 1% that you need to pay attention to. Last week, we saw some crazy news about a big underground structure that's supposedly underneath the Egyptian pyramids. What's new and what are we to make of this? The recent news is about the 3 Great Pyramids in Giza in Egypt. On March 15th, a group of 3 researchers held a press conference in Italy in which they revealed a stunning discovery. They say that they've used a new method of tomography, more about that in a minute. From this, they constructed 3D models which reveal new internal artificial structures. And not only this, they also found something underground. Their images, they claim, clearly reveal that structures exist beneath the plateau, extending below the pyramids for approximately 2 kilometers beneath ground level. These structures form a vast area of non-natural constructions following complex geometries. Concretely, they say that the structures are 8 cylinders surrounded by something resembling spiral staircases. These structures structures, quote, descend to a depth of 648 meters, merging into two large cubic structures measuring approximately 80 meters per side, end quote. Big if true, so I've had a look. Unfortunately, there's no technical paper yet, but going by the press release and the earlier papers of the authors, I have a pretty good idea what this is about. Two of these researchers already published a paper in 2022 in which they introduced a new method to analyze structures in the pyramids. They call it synthetic aperture radar Doppler tomography, which is quite a mouthful, but don't despair, it's not as difficult as it seems. First of all, synthetic aperture radar is a widely used technique to track ground movements. Typically, it's done by satellite, though it could also be done by drone or aircraft. You ping a radar across some terrain and track what comes back. You do this again at some other time, calculate an interference pattern between the two results, and that tells you how much the ground has moved. The radar typically uses wavelengths in the range of 10 gigahertz or so that's millimeter waves. These are quite easily blocked by big layers of rock, which is why you have no cell phone signal in the subway. So how do they want to see inside the pyramids and even under them? Here is where things become interesting. They say that they can use the radar images to track vibrations of the surfaces of the pyramids and of the ground, and that these surface vibrations encode what structures there are inside. Tomography means that you can look inside. The reason they call it Doppler tomography is that the vibrations cause a Doppler shift in the frequencies, so that's how they extract them. Technically, this is correct. You can, in principle, reconstruct the inside of an object from its surface vibrations. Indeed, this is used a lot by geophysicists to map out, for example, magma chambers underneath volcanoes. So you see, both the radar method and the tomography are quite standard methods. It's the combination that's new. In their earlier paper from 2022 that was published in a peer-reviewed journal, they said they'd use that to find structures inside the pyramids. The problem with this paper is that there is no discernible relation between the tomography images and the structures that they supposedly identified. I mean, look at this image. On the right is their measurement. On the left, you see overlaid the chamber we know is there. Alas, their signal is elsewhere. They seem to have randomly identified some structures in their tomography images and ignored others. Of course, I'm not the first to notice this. The 2022 paper was widely criticized and mostly ignored for this reason. They had no explanation for how they identified structures from their images. So what's new in 2025 is that they say they let AI do the job. So they didn't identify the structures, a computer did it. How do I know this? Well, for one thing, they said this in the press conference, but also one of the authors wrote a paper about this 2 years ago. Now look, I'm not a geophysicist, but I find this idea extremely implausible. Reconstructing what goes on inside an object from its surface vibrations is also how remote psychoanalysis on social media works, or for the most part doesn't work. In both cases, the major problem is that you need to have measurable vibrations in the first place. Volcanologists do this with seismic waves, which they track by sensors on the surface. Seismic waves typically have wavelengths in the range of 50 or 100 meters. The magma chambers that they map with this method are in that range too, maybe 100 meters near the surface or kilometers deeper underground. While there are always some seismic waves that'll also shake the pyramids a tiny little bit, they're in the wrong wavelength range to identify small structures, and they don't measure in that range in any case. They write in their paper that the frequency range they look at for the Doppler shift is something like 12 kilohertz, which in the stones of the pyramid corresponds to a wavelength of about 24 centimeters. There is no plausible source for these vibrations, which makes it unlikely that they have a signal to begin with. Also, let's do do a sanity check. If this method actually worked, why isn't anyone else using it? Finally, the idea that the Egyptians would base a structure as heavy as the pyramids on something resembling pillars seems completely crazy to me. Let me also add some words on the two guys who've led these studies. Filippo Biondi previously worked at the Department of Electronic Engineering in Glasgow, but no longer works there. He's applied for a patent for the technology. The other author is Corrado Malanga, who, according to his own website, was a university researcher at the Department of Chemistry and Industrial Chemistry of the University of Pisa. He also has a theory of global alien interference that explains alien abductions as follows. Quote, "The abductee in the bottom right part is programmed using an alien active memory, and in the meantime they momentarily take out his sole component, the little red ball." In summary, the story gets a 9 out of 10 on my bullshit meter. I'm not giving a 10 out of 10 because maybe this Doppler method isn't entirely crazy and just needs more work, but I'm pretty sure what they measure is just noise. If I'm wrong and there are 8 pillars underneath the pyramids, it's probably a strategy plan of the European Union. Thanks for watching. See you tomorrow.